In this second tape of the centrifugal pump repair module, what I'm going to be doing is continuing the overhaul procedures that we discussed in the first tape. So I suppose the first thing we ought to do then is to review the status of our pump, review where we stood at the end of the last tape. We said the casing had been opened, and of course the rotating element had been removed. Following this, there was a thorough inspection performed of both halves of the casing so that the need for any repair work could be identified. And then the rotating element we took to a shop, and in the shop we dismantled that rotating element and laid out the parts from it, and we said when we left that these parts were now ready for a cleaning, inspection, and measurement. Well, that's what I'd like to discuss with you in this particular tape, to go through the various steps that need to be performed on the parts from that rotating element in order to determine whether those parts can be reused or whether they need to be repaired or replaced before we can reassemble the pump. Okay, well, let's talk about it then. What do we need to do with these various parts? Well, the first thing required is a careful inspection to determine which parts are grossly damaged or grossly worn so that we don't waste any further time cleaning and measuring those particular parts. In most cases, severely worn or damaged parts, such as this broken wearing ring, will be obvious during the course of disassembly. But rather than discarding the parts at that time, it's good practice to keep them and examine them in conjunction with their companion parts, as we see being done here. This is so where appropriate we can determine the base cause for the failure or the excessive wear and take steps to correct it as necessary. For example, what you see here is a severely worn impeller. This type of damage is caused by cavitation, which is a condition which can occur in the pump during pump operation. So if this sort of damage is observed in a pump that you're working on, it should be reported so that steps can be taken to determine why the cavitation is occurring, and further steps can be taken to correct it when the overhauled pump is put back in service. Following this inspection, obviously failed or seriously damaged components, such as the impeller and wearing ring we just saw, are of course set aside for disposal. So the inspection then continues by repeating the steps that we just described. Each part is visually examined to determine its condition, that is, to determine whether it is badly failed, badly damaged, which would mean it could not be reused, and which would also mean that steps should be taken to determine the reason for the failure and take corrective action as appropriate. Or the inspection may show that the part appears to be reusable. We can't confirm at this point, but we see no obvious indications that the part has failed. If this is the situation, then that part would be set aside so that further cleaning, measuring, and inspection steps could be performed. So at the end of this preliminary inspection, what we end up with is what you might call two groups of parts. One group of parts is those that have either failed, such as the broken wearing ring that we saw, or are worn so severely that they cannot be readily repaired. And an example of this would be that impeller that we saw with the severe cavitation damage. These parts obviously cannot be reused, so after this visual inspection they'll be set aside for disposal and they'll be replaced with new parts when the pump is reassembled. To be done. But what I want to discuss with you is the other group of parts. They have passed the visual inspection, you might say. That doesn't necessarily mean that they are okay for reuse in the pump, but it means there's no obvious signs of distress or damage that would indicate they couldn't be reused. So the next steps that need to be done are first to clean these, then perform another inspection, and finally perform precision measurements as appropriate. Well, how do you go about cleaning parts from the rotating element of a pump? Well, a number of methods may be used. The method used in any particular case is going to be based on the pump that you're working on, the material that the parts are made of, and the parts themselves. For example, in some cases, sandblasting would be an appropriate method of cleaning pump parts. While with other parts, you would want to do something much more gentle, you might say. Perhaps clean them with emery cloth or something similar. So rather than get into a detailed discussion of cleaning methods, I think I'm going to let you discuss that with your instructor to learn the methods that are used in your facility and learn the variations of methods which can be used for different types of parts. Instead, for purposes of our discussion, what I'd like to do is to assume that all the parts of our pump have been cleaned. I'd like to discuss the further inspection and measuring steps which need to be performed on each part. And incidentally, as we discuss each part, I will explain to you how that particular part was cleaned in our example. So the first parts I'd like to discuss are the packing sleeves. And you remember what a packing sleeve is? Well, just to be sure, let's take a look at this drawing, which represents the rotating element of our pump. If you recall, we said this pump had two packing sleeves, one here and one here. And these sleeves serve two purposes. They provide a surface for the packing to ride on. In addition, the way they're installed is to thread them onto the shaft so they hold the impellers in place. Now, as with most of the measurement and inspection steps that we'll be discussing, the first step here is to check the specified dimensions and tolerances in the manufacturer's instruction book. Now, in the case of the packing sleeves, there are two important dimensions which need to be checked: the inside diameter of the sleeve and the outside diameter of the sleeve. So in this example, the workman first checks the inside diameter of each sleeve. The device he uses is a telescoping gauge, or as I usually call it, a snap gauge. It is placed in the ID of what needs to be measured and then expanded while it is slightly off-center. It is then rocked past center to obtain an accurate measurement of the inside diameter. After this is obtained, then this device is in turn measured with an outside micrometer. This then gives an accurate measurement of the inside diameter or bore of the sleeve at the point that the measurement was taken. After this measurement is determined by the micrometer, then the workman carefully notes it down on a data sheet which he had previously prepared. Because I think it's obvious, the way the final determination will be made whether or not this part can be reinstalled in the pump is by noting the dimensions as measured and comparing them to specified values in the manufacturer's instruction book. Now, following good mechanical practice, the workman then takes a second measurement, 90 degrees out from the original measurement. This way he double checks the dimension, and in addition he checks to determine whether or not the sleeve is out of round. Because if it is not, obviously the two dimensions should be the same. Excessive variation between the two would indicate that for one reason or another the sleeve was out of round or egg-shaped, and if this deviation was excessive, the sleeve would be discarded for this reason. After making these measurements on one sleeve, the workman then repeats the same steps for the second sleeve, and for the same reasons, to verify, number one, that the inside diameter is within the specified tolerances in the manufacturer's instruction book, and number two, to verify that the sleeve is not out of round. Now, I told you that I would explain in each case how the parts for our particular pump had been cleaned. In the case of these two packing sleeves, they were initially cleaned with the use of emery paper, simply to get a good idea of their condition. After this cleaning had been completed, grooving was noticed on the outside surface of the sleeves. This grooving had been caused over a long period of time because of the friction of the packing riding against the sleeve. So the final cleaning step in this case was to mount each sleeve in a lathe and take a cleanup cut along the entire length of the sleeves. So at the conclusion of this cleaning, another important measuring step was to measure the outside diameter of the sleeve, and we'll see this step in just a moment. This was important now for several reasons. Obviously, it should always be checked, simply to verify that it's within the specified tolerances in the manufacturer's book. He also has to be sure that he did not remove so much material by taking the cleanup cut that it resulted in reducing the outside diameter below the minimum value allowed in the book. So he measured the outside diameter of one sleeve using an outside micrometer, and as before, carefully noted the measurement on his data sheet. Now, following the same practice as he did when checking inside diameters, he takes a second measurement at the same location, except 90 degrees around the sleeve. As I said, this is the same reason as we talked about before, to verify that the sleeve is not out of round. Now also, due to the length of the sleeve, the workman made a second set of measurements of the outside diameter at the other end of the sleeve. This was checking for taper of the sleeve from one end to the other, because the measurement should be the same along the entire length of the sleeve. And he made 2 measurements at this point, again for the same reason, to verify the sleeve was not out of round. Now in the case of all these measurements, what would be done after he had completed them is comparing each value noted on his data sheet with the tolerances specified in the manufacturer's instruction book in order to make a final determination whether or not these sleeves could be reused or whether they should be replaced. So the final step in the measuring process was to repeat the measuring steps on the outside diameter of the second packing sleeve, and as before, note these values on the data sheet. Well, I think we've covered quite a bit of material. Before we go any further, and while our workman finishes measuring this second packing sleeve, I think what I'd like you to do is to stop the tape at this point, review the material we've been discussing with your instructor. Well, in the last segment, we discussed the measuring steps that were required on the packing sleeves from the pump that we've been working on. What I'd like to do in this segment is to discuss the same steps, that is, the inspection and measuring steps that are required, on a couple of other components off the rotating element. And specifically, I'm going to be talking about impellers and wearing rings. Now, if you recall, our particular pump has 2 impellers, and one of these impellers has already been discarded because of excessive wear and damage caused by cavitation when the pump was in operation. So as I said, that impeller has already been discarded, and it's been reported that the pump was cavitating. So that situation can be investigated and hopefully corrected before the pump goes back into operation. So we're going to see the other impeller, which has been cleaned. We're going to discuss the measuring and inspection steps required. We're also going to discuss wearing rings and the steps that are required on those. Now, if you recall the wearing rings, each set of wearing rings is actually a pair of concentric rings, that is, one inside the other. The outer ring, when the pump is assembled, is held stationary in the case. The inner ring, or rotating ring as it's usually called, is attached to the impeller. And there's a very close tolerance between the rings. So that's one measurement we're going to be seeing, how we determine what that tolerance is, to determine whether the rings can be reinstalled or need to be replaced. So before we go out to the shop, let's take another look at my drawing here and identify the components that we're going to be discussing. Although we'll only see one in the shop, our pump has 2 impellers, one here and one here. And it has a total of 4 sets of wearing rings, one on each side of this impeller and one on each side of the other impeller. Now, just like with the packing sleeves we saw earlier, the first thing our workman does is to determine the specifications and tolerances from the manufacturer's instruction book and transfer this information to the data sheet that he will use for his measurements. Then, using an inside micrometer, he measures the inside diameter of one of the stationary wearing rings. And, of course, he logs this measurement on his data sheet. He then repeats the measurement on the same ring, except 90 degrees from the first measurement. This is to check and determine whether or not the ring is egg-shaped. This reading also is logged on his data sheet. And these steps are repeated, of course, for each stationary wearing ring. After measuring and logging the inside diameter of the stationary wearing rings, the workman then needs to check the outside diameter of the rotating wearing rings, which of course are attached to the impellers. So he makes use of an outside micrometer of the appropriate size in order to measure the outside diameter of the ring. Like all the other measurements, once this one has been made and carefully checked, it too is logged on the data sheet that he prepared for this particular pump. And again, following good practice, as when measuring any circular device, he takes 2 readings, one 90 degrees out from the other. As I said earlier, this is a double check to determine whether or not the ring is egg-shaped. And this reading, too, once taken, is logged on the data sheet. Now, there's one other important dimension to check on a pump impeller, and this is the inside diameter of the opening, or bore, in the center of the hub, that is, the opening which fits over the pump shaft. This needs to be checked to be sure that the diameter is within specifications, so that the impeller will not be too loose on the shaft, and it too needs to be checked to determine whether or not it's egg-shaped. So to take this measurement, he uses a telescoping gauge or snap gauge together with an outside micrometer. He inserts the snap gauge in the bore, releases it, and then after relocking it, rocks it past center, then removes it and measures the resulting dimension using an outside micrometer. And of course this measurement, like all the others, once taken, is logged on the data sheet. And this measurement too will be repeated 90 degrees out from the first to check for an egg-shaped hole. After completing these measurements, the workman then turns the impeller over so he can get access to the other side. Once he has done this, he will measure the rotating wearing ring on the other side of the impeller, and he will again measure the hole or bore down the center of the hub. This measurement is checked on both sides to check for taper. Now you're probably wondering how we cleaned the impeller from our pump. As is frequently done, we cleaned it with a sandblaster. However, we did mask the wearing rings before doing this so that they would not be sandblasted. The wearing rings were cleaned separately using emery cloth. Well, we've seen a number of measuring steps performed, and our workman now has, as the result of this measuring, a set of data on his pump data sheet. However, when it comes to wearing rings, there's one more important data step that he has to perform before the measuring job is really complete. In order to determine wearing ring clearance, the workman must take the outside diameter of each rotating wearing ring and subtract it from the inside diameter of its companion stationary ring. This difference, then, is the actual clearance between the two rings, and this is what's compared against the specifications in the manufacturer's instruction book. Well, with that, I think we're again up to a pretty good stopping point. We've covered the information I wanted to regarding the inspection and measuring steps on impellers and wearing rings. And before we discuss another component, what I'd like you to do is to stop the tape and review what we've been talking about with your instructor. In this segment, I'd like to talk about the precision measurements that are required on the pump shaft. As I'm sure you're aware, the pump shaft is what you might call the heart of the rotating element. That is, it passes all the way through it, and this is the part that supports the rotating element, and the part that all other parts, such as the impellers and sleeves and so forth, are attached to. Now, there are two primary measurements that we have to make on the pump shaft. First, we have to check what's called runout, which is the degree of straightness of the shaft. And we also have to check the shaft diameter. And as we're going to see, this has to be done at a number of locations because we have different diameters at different locations. We might have one diameter out here for a bearing journal, a different diameter under this sleeve, and a third diameter perhaps under this impeller. So each diameter has to be checked for both runout and dimension. Now, as before, the specifications, of course, are determined from the manufacturer's instruction book. So first, let's talk about measuring shaft runout. Now, in order to do this, the bare shaft is mounted up in some mechanism which will allow it to be turned and hold it perfectly straight at the same time. One way of doing this is to put it in a set of pedestal rollers, as we see here. Another alternative might be to mount it up in a lathe. In any event, with the shaft securely mounted and free to turn, we then make use of a dial indicator. Set the dial indicator on position, in the position that we want to check, and then slowly turn the shaft through a minimum of 360 degrees and measure the deflection of the meter. This measurement then is repeated at each diameter of the shaft in order to determine the runout of each surface. In addition to this, we also take runout measurements on each shoulder of the shaft, that is, at each location where the diameter changes. Because if we have an out-of-round condition here, the part that seats up against the shoulder will wobble when the shaft turns. Now, of course, the results of all these runout checks are logged and compared to specified values in the manufacturer's instruction book. Now, if we find excessive runout, that is, the shaft is not straight enough to meet the specifications in the manufacturer's manual, then that really concludes our precision measurements of the shaft, because that means the shaft will probably have to be replaced. But if we assume that our shaft has passed the runout check, that is, the runout at each location that we checked, on each diameter and on each shoulder of the shaft, falls within the specified values, then we can proceed to make the second check which is a measurement of the diameters at each shoulder on the shaft. Before beginning the actual measuring steps, the workman places a series of reference marks on the shaft. As with the procedures we've discussed earlier, he will be taking two measurements at each diameter, 90 degrees out from one another, in order to check for roundness. However, since the shaft is free to turn in the pedestal rollers, he places reference marks so that he can keep track of where each measurement was taken. So he placed a series of reference marks on the shaft and then turns the shaft 180 degrees and places another series of marks on each diameter. Now, after he has completed marking the shaft, comes a very important step. He needs to check, again, the manufacturer's instruction book to determine the specified tolerances for each diameter on the shaft and to verify that he has transferred this information from the manufacturer's manual to the data sheet that he's using for his measurements. So he checks the manufacturer's manual, which, as I said, will have specified values and tolerances for each diameter, and verifies that this information is on his data sheet, because these are the numbers that he needs to compare to his actual measurements to determine whether or not the shaft is reusable. After doing this, he then begins to measure the various diameters of the shaft. And the first measurement he performs is on a sleeve in the center of the shaft. Now, the purpose of this sleeve is to establish the proper distance between the two impellers when they're installed. He takes the first measurement at his reference marks. Using an outside micrometer, he obtains a measurement at this point and, of course, logs it on his pump data sheet. He then repeats the same measuring steps, except 90 degrees out from the original measurement, and he does this by referring to his reference marks. As I said before, this is a check for roundness. However, I should point out that any significant out-of-round condition should have been caught earlier when he performed his run-out checks. So this is really a double check at this point to verify that the shaft does not have an out-of-round condition at any of its diameters. After performing this second measurement and logging its results, he's then ready to move on to another diameter on the shaft. The next measuring point he chose was the bearing journal on the outboard end of the shaft. And as before, he will take two measurements, one at his reference marks and the other 90 degrees out from the reference marks to verify that the shaft is not out of round. Now, as usual, I should say a few words about the cleaning of this particular component. In most cases, minimal cleaning is required of a shaft. In this case, the shaft is essentially the same as it was when removed from the pump, although certain areas of the shaft were cleaned with emery cloth before these measuring steps. Well, I think while our workman finishes the measurements of this particular shaft, what I'd like you to do, as usual, is to stop the tape at this point, take a short break, and review shaft measurements with your instructor. Well, I think in the previous segments that we have covered all of the parts which are directly attached to the rotating element. But there are other parts associated with the rotating element which we also need to discuss in terms of the inspection and measurement steps that are necessary on those parts. Now, the first of these I'd like to talk with you about are the seals, which are used to seal the points where the shaft penetrates the pump casing. So again, let's take a look at a drawing of the pump that we're working with, see what we're talking about here. Now, in our particular pump, the shaft comes through the casing at two locations, here and here. It's a fairly typical arrangement. And of course, both of these locations need to be sealed to prevent either liquid getting out of the pump or air being drawn into the pump. Now, in some pumps that you may be working with, you'll have mechanical seals, in which case, in the course of pump overhaul, those seals will be dismantled, inspected, and repaired as necessary. But if you recall, our particular pump makes use of conventional packing at each end. So what we see here represents the rows of packing. We also see a lantern ring installed and a connection. Okay, well, the reason for this is we inject seal water at this location on our particular pump. And of course, a gland follower is installed in order to adjust the packing. Well, the packing itself, of course, has been discarded. but the lantern rings and the gland followers have been cleaned and are ready for inspection. Now, as with most pump components, there are a number of methods that can be used to clean gland followers and lantern rings. In the case of our particular pump, they were cleaned using a sandblaster. Since these are not precision parts, no special measuring steps are required. Instead, what's required after the parts have been cleaned is a visual examination to determine whether they need to be replaced or whether they can be reused. Now you notice this workman, after examining and approving the first gland follower, places it in a plastic bag together with a tag which identifies the part and is marked OK. This signifies that the part has been inspected and is OK for reuse. He then proceeds to inspect the second gland follower. Now what he's looking for in his inspection is evidence of excessive wear, such things as erosion or wire drawing, gouging, pitting, cracking, and so forth. Finding none of these, this gland follower also is placed in a plastic bag and will be identified with a tag, which will be marked OK, saying that the part has undergone inspection and is OK for reuse. And the tag, of course, will identify this particular part. Now, this careful bagging and tagging takes a little time now, but as we will see, it makes reassembly of the pump later on much easier, because each part is clearly identified as to where it came from and, of course, where it should go. Now, following his inspection of the gland followers, the workman then proceeds to examine and inspect the lantern rings. You recall this particular pump has two-piece lantern rings, so there's actually 4 parts to inspect. And he's looking for the same sorts of problems here: cracking, pitting, erosion, or other signs of excessive wear. And again, after examining each lantern ring, it goes in its own plastic bag with its own identification tag marked OK. This way, each part can be reinstalled in the same location that it was removed from. And of course, following this, the same steps are repeated for the remaining lantern ring. Well, that takes care of the steps involved in the seals on our particular pump. Now, another very important component, related but not directly connected to the rotating element, are the pump bearings. And as we're going to see, there are a number of inspections and also some measuring steps involved in the different components of pump bearings. So let's review the bearings that are installed on our pump. If you recall, we had 2 sleeve bearings, one installed on the inboard or coupling end of the pump, and the other installed on the outboard end. And in addition, on the outboard end of the pump, we have a multi-disc thrust bearing. Well, the components I'd like to talk about for the moment are associated with the sleeve bearings. We have oil seals, if you recall, which are little discs installed on the shaft and rotating with it. And we also have lubricating oil rings to circulate oil for the bearings. So first, let's talk about an inspection of the oil seals. In most cases, the only cleaning required on bearing oil seals is to wipe them off with a rag. However, once they have been cleaned, they should be carefully examined for any cracks or chips and replaced if any are found, because a faulty bearing oil seal will of course result in a loss of oil from the bearing. Now you'll notice that as with the other parts, after inspecting them, the workman places each seal in a plastic bag together with an identification tag which he writes on to identify the part and also to signify that it's been inspected and is okay for reuse. These steps, of course, are repeated for each bearing oil seal. Well, we've seen an inspection involving the oil seals for our sleeve bearings. Now let's talk about the inspections required for the oil rings. It's extremely important that these bearing oil rings, or slinger rings as they're frequently called, be carefully inspected. As with the oil seals, they require no particular cleaning other than perhaps wiping them off with a rag, but they should be very carefully examined for any burrs or anything else that would prevent free motion. Now, as you recall, these rings ride directly on the shaft and should be free to turn. Anything on their inside diameter which would restrict their movement might cause them to hang up, and if they do hang up while the pump is in operation, there will be insufficient oil to lubricate the bearing. So they should be visually examined with particular emphasis on their inside diameters to be certain that there are no burrs, chips, or anything like that which might restrict free movement of the rings. Now you'll notice, as with the other small parts, after examining them, the workman bags them together with an identifying tag. We've covered quite a bit of material. There are obviously some more steps involving bearings, because we haven't even discussed bearing shells yet. But I think what I'd like you to do for the time being is again to stop the tape and review what we've been discussing with your instructor. In the last segment, we saw some inspection steps involved in the bearings on our pump, or you might say accessories for those bearings, the oil seals and the oil rings or slinger rings that provide oil circulation in the bearing. Well, in this segment, I'd like to talk with you about the bearings themselves. And we're going to be talking about a very specific item that needs to be checked on these bearings before they're reassembled. And that item is called oil clearance. And what this means is the difference in size or diameter between the journal, which is the shaft itself, which rides in the bearing, and the bearing or babbitt material itself, which I usually refer to as a bearing shell. Now this clearance is there, as the name implies, to allow oil circulation in the bearing. Now we already know part of this dimension, because as we've already seen, using a micrometer, we measured the diameter of the bearing journals on the shaft for the two sleeve bearings. We need to determine oil clearance for both the sleeve bearings and the thrust bearing on the pump that we've been working with. So what we're going to be seeing is some measurements for the outboard bearing on our pump, because if you recall, that outboard bearing had a shell which served double duty, you might say. It provided the babbitt or bearing surface area for both the sleeve bearing and for the thrust bearing on that end of the pump. Looking once again at the drawing of our pump, we can see that this area of the shaft serves as the journal for the outboard sleeve bearing. But then attached to the end of the shaft is the thrust collar, which contains the discs of the multi-disc thrust bearing. Well, these discs are riding in an extension of the same babbitted shell. As with the other measurements that we've discussed in this program, the first step the workman performs is to determine the specifications in the manufacturer's instruction book and then transfer these numbers to the data sheet that he will use for his measurements. Now, the first measurements that he performed were involved in determining oil clearance for the thrust bearing. As you can see, he has the two halves of the bearing shells apart and on the table. And then using a vernier caliper, he measures the size of the grooves into which the discs of the thrust bearing collar fit. Now, as you can imagine, this is going to involve a number of measuring and recording steps, because what's required in order to accurately perform this check is to measure each groove twice in each shell. So that's a total of 4 measurements for each thrust bearing groove. And of course, each of these 4 measurements for each groove must be recorded, and must be recorded in such a way that he can keep track of which groove the measurement goes with. After completing the measurements of the thrust bearing shells, and of course logging the results, the workman then measures the width of the discs on the thrust collar, again using a vernier caliper. And these readings too, of course, are logged on his data sheet. Then the final step, after all measurements have been completed, is to subtract the width of each disc from the measured width of the groove in which the disc fits. And this difference is the oil clearance for the thrust bearing. In order to check oil clearance on the sleeve bearing, the workman must first assemble the two halves of the bearing shells in order to measure the inside diameter of the assembly. So he places them vertically on the table, pushes them together, and then clamps them together using a hose clamp. This way he can measure the inside diameter of the babbitt or bearing surface, which of course he will compare to the outside diameter of the bearing journal on the shaft. And the difference between these two measurements will of course be the oil clearance for the bearing. So after assembling the two halves of the bearing shell together, the workman then makes use of a snap gauge and an outside micrometer in order to measure the inside diameter of the shells. And this is done following the same procedure as we've seen earlier. The compressed snap gauge is inserted into the opening, released, and then reclamped, and rocked past center in order to obtain an accurate measurement of the inside diameter. snap gauge is then removed from the opening and measured using an outside micrometer. And as before, the results of this measurement will of course be logged on the data sheet that he's been using for the bearing checkout. Now once this measurement has been made and recorded on the data sheet, it too will be repeated 90 degrees out from the original measurement for the same reason that we have described in earlier measurements, to check and be sure that the bearing is not out of round, because it will have an allowable tolerance for clearance and another allowable tolerance for roundness. If the bearing is too far out of round, then the shaft will move in the bearing as the pump operates. And as before, I might say a word or two about how these parts have been cleaned. In most cases, bearing parts require minimal cleaning. Usually, the only cleaning that's required is to wipe off any excess oil with a rag. Now, of course, the sleeve bearing on the opposite end, or inboard end of the pump, would be checked in just the same fashion as the one we've just seen. And I think with that we have covered all of the measuring and inspecting steps that are required on a disassembled centrifugal pump. But before I close, it might not hurt to review the various steps that we've been discussing on this tape. Now, if you recall, we started out with a discussion of the packing sleeves, where we measured and recorded the inside and outside diameter of these sleeves. We also discussed inspecting and measuring the impellers. We measured the inside diameter of the opening of the hub, which passed over the shaft, and we also saw measuring steps involving the wearing rings. With regard to the shaft itself, we again had two checks to perform. We checked runout of the shaft, which we said was a measurement of the degree of roundness or straightness of the shaft. And we also measured the dimensions of the shaft at each diameter and compared these to specifications. With regard to the pump seals, in the case of our pump, we used conventional packing seals. So all that was required after cleaning was a visual inspection of the gland followers and also the lantern rings. Now, we had several bearing components we discussed. We saw a visual inspection of the bearing oil seals and also a visual inspection of the oil rings or slinger rings from each bearing. And then finally we discussed checking the bearings themselves, and this involved measurements of both the thrust bearings and the shells for the sleeve bearings, which were compared against readings previously taken on the shaft. So following these measurements and inspections, and of course the casing inspection that we discussed in the first tape of this program, we should now have identified any components of the pump which are in need of repair or replacement. Any obviously failed components, of course, would be replaced. Components which failed to meet specifications may be repaired or replaced, depending on the particular component and how bad it is. All of these things, of course, must be done before we begin reassembly of the pump. And that's the next thing I'd like to discuss with you, how we go about putting this pump back together again. But I think what we'll do is hold off that discussion for a short while. You'll find that beginning on the next tape of this program. But for now, what I'd like you to do is to stop and review what we've been discussing with your instructor.